One technique that's going to be helpful for us to evaluate integrals and other sorts of problems later in mathematics is being able to do a technique called completing the square, which you may remember from pre-calculus or a class like that. And so to complete the square, what you're going to have to do is you're going to have to try to put something into, or a polynomial into this form. So it would be a square minus 2ab plus b squared. All right, and this is a perfect square trinomial because that turns into a minus b squared. Or if you had a squared plus 2ab plus b squared, that'll factor into a plus b squared. All right, so going back to like your algebra 2, these are perfect square trinomials. And that's the goal, is to try to rewrite something into that form if it doesn't necessarily look like a nice substitution immediately. Okay, so what we're going to do is we're going to complete the square, then we're going to use a substitution, and then we're going to use a trig substitution. So these are like double substitution problems. All right, it sounds like really difficult, but a lot of times these aren't too bad. So let's take a look at a fairly elementary example of this. We have the integral of dx over the square root of x squared minus 6x plus 13. All right, so here's how we're going to do this. We notice that if this was just x squared plus 13, so if that 6x wasn't there, then at least we could say that maybe x, like for instance, if that 6x wasn't there, it was just x squared plus 13, then we could at least say that x would be equal to root 13 of tangent, but that 6x is there. All right, so we can't pretend. But let's do this. Let's think about this and rewrite. And we know that the form is going to be a squared minus 2ab plus b squared. And so if we were to able to get to something that had that form, then what we could do is we could be able to factor it and then maybe do a substitution. All right, so to get there, here's what we're going to do. I'm going to take the middle term, and this is a common technique for completing the square. And what you do is you take half of the coefficient and you square it. And that's what you're going to need to be able to complete the square, at least if it's a single variable. Now, if it's more than one variable, then, well, then we're in Calc 3. We wouldn't need to be having this problem. So in this case, what we're going to do is we're going to say, all right, well, that's going to become dx over the square root of x squared minus 6x. And if we take half the middle coefficient, that's negative 6 over 2 squared, which is going to be 9. So what I'm going to do is I'm going to add 9 and subtract 9. All right, and that's a common technique in mathematics. We still have that 13 there. All right, and the whole reason I do this is because now this is a perfect square trinomial, and we could just factor it. Okay, and so to factor it, what we're going to do is we're going to rewrite this as dx over the square root. This whole thing now becomes x minus 3 squared, and then we have negative 9 and 13, which just turns into 4. Right? So that's completing the square, and you might be thinking, okay, well, that doesn't really do much because I still haven't gotten rid of everything I need to. So now what you're going to do is you're going to do a u substitution. So let's let u be equal to x minus 3, what's in the parentheses. And then du is going to be dx. And that might be weird to think of it that way, but what we end up with is we end up with du over the square root of u squared plus 4. And now this is a perfect trigonometric sort of substitution problem. In fact, we're going to use the same substitution in the previous, where we have a is equal to 2, because we take the square root of that 4 and that gives us 2. It doesn't always work out perfectly, but in this instance, it was really nice. And so our trig substitution is going to be that u is equal to 2 tan of theta, u over 2 equals tan theta, and then our derivative du is going to be 2 secant square of theta d theta. And for our triangle, we already know it's the same triangle as before, okay, except in terms of instead of x, we're going to have u's. Remember, tangent is opposite over adjacent, so that's going to be u and 2. And then this is going to be the square root of u squared plus 4 by using our Pythagorean theorem. Okay? Now we're ready to do the substitution. Okay? And you're actually going to find that this works out really nicely for this one. And so our integral, instead of du, we're going to have 2 secant square of theta d theta. In the denominator, square root of 2 tan of theta square plus 4. And as we do with all the other problems, let's just go ahead and simplify the radical. So that's going to be the square root of 4 sec square theta plus, or sorry, tan square theta, getting ahead of myself, because I know it's going to work out to be a secant. So this is going to be 4 tan square theta. We can factor out the 4, and we have 4 tan square theta plus 1. And then that becomes 4 sec square theta or 2 sec theta. All right. And that makes this a really nice problem. All right. So now we end up with 2 sec square theta d theta divided by, this is just going to be our 2 secant of theta. All right. We still have some back substitution, but at least we're getting to the point where this is going to be nice. 2's cancel out, one of the secants cancel out, and we're left with the integral of sec theta d theta. All right, this is basic. All right, that's where we might want to go back to that list of integrals that's on that card. Okay. So now this is going to be the natural log of the absolute value of secant theta plus tangent theta plus our constant of integration c. We have to do 2 substitutions, okay? So remember that secant is going to be hypotenuse over adjacent. Tangent is going to be opposite over adjacent. And now what we can do is go back up to our triangle. Okay, so hypotenuse, remember, is u squared plus 4. Adjacent is 2. And then opposite is u. All right, so we need all 3 of them to substitute back in. So now we're going to get the natural log. We're going to have the square root of x squared plus 4 divided by 2. The opposite, I'm sorry, it's going to be u squared plus 4. And that's going to be u over 2 plus c. All right, so last thing we need to do is we need to back substitute. Okay, and so this would end up being the natural log of the square root. And remember, u was equal to x minus 3 all the way back here. Okay, so remember we had u was x minus 3. So a couple possible finished solutions, one of which x minus 3 squared plus 4 over 2 plus x minus 3 over 2 plus c. This is a perfectly acceptable answer to me. However, sometimes in the computer algebra systems, of course, they're going to simplify it. And I just want to make sure that everybody's okay with how we simplify this. All right. Another way to write this would be the natural log of the absolute value. We can factor out a 1/2. And then we can also expand this x squared minus 3. So that would be the square root of x squared minus 6x plus 9 plus 4. So that's going to be x squared minus 6x plus 9 plus 4 plus x minus 3 plus c. And you probably remember that there's a rule that says if you multiply a logarithm, the absolute value should be before the c, excuse me. There's a rule that says if you multiply within a logarithm, you just change it to addition. So another way to write this would be natural log of 1/2, okay, or you could divide it and subtract, plus the natural log of the absolute value of square root x squared minus 6x plus 13 plus x minus 3 plus c. All right. And now this is what the computer algebra system will usually do is they like to meld constants together into bigger constants. All right. Or I don't want to say bigger constants, but simplify it. And notice that ln of 1/2 is a constant and c is a constant. And so what a computer algebra system would probably do is just meld those together and write the final answer as ln absolute square root x squared minus 6x plus 13 plus x minus 3. And I'm just going to call this C1. All right. But just be careful. Okay. In your My Math lab, they might want you to call it just C. It really doesn't matter. All right. I'm just calling it C1 because I know that C1 is going to be equal to ln 1/2 plus C. All right. This is probably going to be the most simplistic answer that you can get. And when I say simplistic, of course, I'm putting that in air quotes because there's nothing simple about it. Okay. So steps to be able to do this. Okay. Going back. Okay. Remember, this is a completing the square problem. Okay. Because it's not x squared plus 13. Okay. Or x squared plus 4 or something like that. We just have like a linear term that kind of separates those. So in those instances, you do your completing the square. And completing the square, you take half of the x coefficient and square it. That's what you're going to add and subtract. And then from there, you complete the square and do a u sub. And then the problem should become just a normal trig sub after that. Okay. All right. We do have one more example, which we're going to do in the next video.